Good evening and welcome to our first online webinar organized by the Young Chemists. Today we are pleased to welcome Professor Jérôme Cornil from the University of Mons. Before starting our webinar, we would like to take the opportunity to present ourselves and what we do. So we are the Association of Young Chemists of the Royal Chemical Society in Belgium and more specifically in the Federation Wallonia Brussels. Our goal is to help young chemists, mainly master students, PhD students and postdocs during their first step in a scientific career. How are we doing this? Mainly by organizing various events throughout the year, such as conferences, where we give the opportunity to young researchers to present their work and to exchange with peers, by organizing lectures, such as the scientific lecture of today, or lectures where we inform more about the best way to valorize your results and your personal skills. We also inform about job opportunities. We do, for example, company visits so that you can get more familiar with the local chemical industry. And we also publish lots of job offers on our social media accounts. So our goal is really to create a link between academia and the local chemical industry so that fruitful collaborations can be maintained and that you can find easily a job after your studies. We would also like to provide networking opportunities. Usually once a year we organize a badminton tournament, but as you know, this year this wasn't possible because of the sanitary crisis. So we are always looking for new opportunities to still enable you to exchange with peers. For example, during this kind of online webinars, but we would also like to give you the opportunity to present your research work and to gain some credits for your doctoral formation. So we will be organizing a competition for the best video clip, where you can present your research with an original and attractive video of 3 to 5 minutes for a scientific audience. This competition will be open to all chemistry PhD students. It is worth credits, and the best video will even be awarded a big prize. So if you're interested or if you have questions, just let us know and send your video clip at least for the 1st of March. If you have any more questions, you can always contact us per email, and you can also find information on our social media accounts on Facebook and LinkedIn. Now let's talk about the webinar of today. We are very happy to welcome Professor Jérôme Cornil for this first online webinar. As a little introduction, he obtained a PhD in chemistry at the University of Mons, and afterwards he did 2 postdoctoral stays at the University of California, at Santa Barbara, and then the second one at the MIT Boston. In 2000, he came back to the University of Mons as a senior FNFS researcher. His research interests mainly deal with the theoretical characterization at the atomistic level of the structural and electronic properties of organic and hybrid materials, and this especially regarding their use in energy applications. So if you have questions during this webinar, just send them in the question section and we will try to ask them at the end of this seminar. Thank you very much for taking the time, Professor Cornil, and the floor is yours.
Okay, good afternoon, everyone. And first of all, I would like, of course, to thank the Young Chemists for the invitation. And of course, it was for me a great pleasure to accept it. So today, as promised, we will embark for a journey into the world of organic electronics. And this is a field also initially called plastic electronics. So when we think about plastics, we have, we have in mind materials that are typically used for their mechanical properties because they are light, they are flexible, it's very easy to process, they have low cost. But of course, those plastics will not be useful for us because they're not going to conduct electricity. And the reason is seen below, we have a typical polymer here called polyethylene. And let's do a little bit of chemistry. Here, each carbon atom is connected to 4 neighbors. So all the valence electrons are used to make bonds with the neighbors. And basically, the electrons shared by the nuclei, between the nuclei, they help to give a stability to the backbone of the molecule to make strong bonds. And these are the standard polymers that everybody knows. Now, in the field of organic electronics, we will deal with a different family of material called conjugated polymer. And here you see that the main difference is that each carbon atom is connected to 3 neighbors. And there is an extra electron, a pi electron for the chemist, which is basically not involved in the formation of strong bonds between the atoms. And this electron can basically move along the backbone of the molecule. This is the same for each carbon atom. Each carbon atom is providing a pi electron, and those electrons are not used for the stability, and they can move along the backbone quite easily. So you already understand that these pi electrons will be responsible for all the properties that I'm going to show you today. So thanks to these pi electrons, those conjugated polymers or small molecule, so we will call them conjugated materials, they are falling into the category of semiconductors in terms of electrical properties. And this is some basic, but we will need them in the following for the understanding of the different concepts. So typically all the pi electrons are forming electronic levels with a well-defined energy. There are many of them which are filled, making a box like that we will call the valence band. And on top there is an empty box with a lot of electronic levels, but they are not occupied. And of course, if there is a small gap between those 2 boxes, with some energy, the thermal energy, you are able to excite electrons from the valence band to the conduction band. Why is it important? Because if you have a lot of, let's say this is a polymer chain, and you want to have a charge transport between chains, of course, there is no chance to transfer an electron from one chain, from the valence band of one chain to a neighbor, because everything is occupied here and also in the neighboring chain. So the only way to get a current is to make some room for charge transport. And if you excite thermally, then you end up with an electron in an empty box. And of course, this electron can start jumping from chain to chain and give rise to an electrical current, an electron current. And when you excite the system, you also create a free place here in the valence band, an empty slot, a hole, and an electron jumping from a neighboring chain can fill this hole. And in a sense, you have also a hole moving between chains. So you have positive charges responsible for the charge transport. So you have 2 different origins for the current: electron transport within the conduction band by hopping between chains, and holes within the valence band. Now, if the gap between those 2 bands is very large, there is no chance with thermal excitation to generate carriers, to have a current. So these are the insulators, like the standard polymers that we know. If you have a metal, in contrast, there is no barrier between the 2 bands. So it's very easy to transfer electrons in the conduction band and to generate a very high electrical current. But of course, if you just rely on thermal excitation, you will not make practical devices. So what we are going to do in our devices is actually to encapsulate, to sandwich the conjugated materials between 2 metals, 2 metallic electrodes. And these are the metals because there is no gap between the valence band and the conduction band. And let's say these are my polymer chains. Of course, there are billions of them in the active medium. And initially, there is no chance for having a current because you want to transfer electron from here, the Fermi energy, the top of the valence band, to the empty conduction band, but there is a barrier. And the same, if you want to create a hole here, you need to remove an electron, but there is also a barrier. So now the trick is to apply a bias, an electrostatic potential. And if you apply a bias between the two metals, you are going to shift the Fermi levels. And thanks to that, on one side, you are going to make a kind of resonance and to inject electrons in the conduction band, and you will have an electronic current. And typically, you don't do both at the same time, but if you get a resonance on the other side, you can remove an electron, create a hole, and the hole can also move and make a positive current, but also an electrical current. So in all the devices that we are going to discuss, we are going to inject the charges in the material from metallic electrodes. So the field of plastic electronics goes back to the year 1980s, when there was a very important discovery made by a young student in Japan. He was asked to make the synthesis of a polymer, which is called the trans-polyacetylene. So this is an alternation of single and double CC bond. And okay, he did some mistakes in the ingredients, in the ratio of the different reactants, and he ended up with this kind of material, like a metal, but it was really a polymer. And this material was able to transport current very, very efficiently. Actually, then we realized that what this student did was to make a redox reaction between the polymer and redox agents. And by removing electrons from the polymer, well, the polymer chains became electrically conducting. And the conductivity was boosted from a very, very small value in the pristine, the initial state, to a very large electrical conductivity, similar to copper, a very good metal, by this kind of chemical doping. And this discovery was awarded by the Nobel Prize in Chemistry in 2000, and was basically the origin of all the further developments in the field. So these were at the time very fascinating material, because they have all the properties of plastics. They are light, they don't cost too much, you can tune the chemical structure, but they have also a high conductivity. They can transport electricity very efficiently. It's very easy to use many redox agents to dope them, to make them conducting. And since you remove pi electrons, you don't touch the stability, you don't affect the stability of the backbone. So people were thinking about a lot of applications, like making batteries with these polymers as electrodes, making electrostatic coatings, which are transparent coatings that would dissipate the electrostatic energy, because this is a conducting plastic. So there were some minor success, but there was no real competition with the existing material. And so, okay, it was not a big success. And so we had to wait a few years until 1990s, when people came back to those kind of material. And now we are going to use them in the neutral state, so they are not chemically doped in the following. And so there was an interesting experience made in 1990 at the University of Cambridge. So it's a simple device. You take a glass substrate, you deposit ITO. ITO is a very specific material. It's transparent and metallic. Then you deposit a conjugated material, like a polymer chain, a conjugated chain, and then you evaporate a small metallic contact. And if you apply a bias between those two contacts, you get some light coming out from the material, from the organic material. And this is the beginning of what is known now as the Oled technology. So it's an organic-based light-emitting diode. Okay, what is the principle? We will go quickly, but you will see that it's not easy to make light from organic material. So basically, you have to apply, this is the two electrodes here, aluminum on one side, the ITO on the other side, and they have different Fermi energies. The Fermi energy is the border between the valence band below and the conduction band above. And in between, you have the polymer chains. There are many, many of them. And when you apply a bias between the two electrodes, what you are going is to generate an electric field and this electric field will make, this is back to physics, a gradient of the energy potential. This should be seen as the bottom of the conduction band of the polymers are changing across the material. Now, thanks to this kind of toboggan, you can inject electrons from this contact, and the electrons are going to migrate down the hill. You can remove electrons and create a hole here, and they are going to migrate under the influence of the electric field. So we talk about injecting, migration, and at one stage, the hole and the electron will be on the same chain, and the electron in the conduction band here will be happy to go down to the empty place here, to the hole, and the extra energy will be released, hopefully by emitting some light, but also possibly by emitting some heat, which is not wanted in the device. So you need to have recombination and a radiative decay. This is what we are looking for. And then there is the hot coupling, because you can generate light in the device, but it can be reabsorbed before leaving the device. And this is a major issue, that you need the light going out of the device for the people, for the audience. And so you need to find the right material. This research has been pursued for many, many years. Initially, everybody was using fluorescent material, but there was a big issue. The fact is that when the electron and the holes meet, they don't know anything about the spin they have. You know that electron is a spin up or spin down. And so they can basically recombine into singlet or triplet excitation. In a simple picture, in triplets, you have the two spins parallel. In singlet, they are in opposite direction. Another thing is that for most of the fluorescent molecules, first, quantum mechanics is teaching us that when you have recombination, you will make 3/4 of triplet and only 1/4 of singlet. But the bad news is that all the triplet excitation, they cannot recombine radiatively, because for light molecule with carbon, hydrogen, you would need to reverse the spin to go back to the singlet ground state. And this is very slow and mostly forbidden for many, many small molecules. And so you lose automatically 75% of the charges that have recombined. It's a bad news. And this put the limit of the efficiency to 25%. So there was then a second generation. And the idea was very bright. The people said, okay, there is a class of material which can basically favor the phosphorescence going from the triplet to S0. And with a very specific ingredient, which is called spin-orbit coupling, which is a relativistic effect, you can go from T1 to S0. And the trick to get this process efficient is to have a very heavy atom, like a metallic atom in the center, like here, like it's an iridium here. And so in those light-emitting devices, you generate 25% of singlet, 75% of triplet, but then thanks to this coupling, you can have a transition from S1 to T1, and then you can exploit all the T1 for light emission, and you have 100% efficiency if everything goes well. Of course, there are other problems, but you can exploit all the excitations that have been generated. So this is basically what you find right now in many, many devices, typically sold in Japan, like the mobile phones, like the camera, like any kind of music application, a reader, you will find this kind of material. But the thing is that the metallic center, they cannot be used for very large application because they are toxic and they are not really earth abundant. If you want to develop the technology, you don't want to play with metallic atoms. And so there was a third generation that we are currently developing. And the idea is to design fully organic materials without this heavy metal and with a very small energy barrier between S1 and T1, so that even though you generate T1, you can go back to S1, and then you get a very significant emission, a fluorescence signal from all the excitation. This is the new generation. So this Oled technology has many advantages. It's very easy to change the color of the light emitted because you have just to change the chemical structure. It's stable over many cycles of emission. You will see that you can make devices flexible because you have a major plastic or organic component. You can deposit very large areas, which is not the case with the LED technology, for instance. But the bad news is that they're very sensitive to degradation by species like oxygen and water. And so they have to be made the device has to be made in a glove box and then encapsulated before being used in a real application. But with that, the device can live for a long time. So to illustrate those advantages, yes, you can make basically all the possible light you want for a color TV display, a color display, just by changing the chemical structure. And you have a lot of advantages using those materials, and you can do the technology with small molecules, with polymers. It's up to the company, and there are pros and cons in each situation. When you do polymers, the best advantage is that you can work with solution. So you can deposit the material from solution. You can print your device on a substrate, which is very neat. But if you need many layers, it will be difficult to stack many polymer layers because there is a risk of dissolving the previous layer that you have deposited. You can play with small molecules. This is done typically in Asia, and this is nice because you have well-defined structure. You can make multi-layer, but of course you need a vacuum processing, which might be not the best idea if you want to reduce the cost of production. So you have two different technologies. It depends on what you really want to do. And so this OLED technology now is found in many applications like camera, mobile phones, any kind of reader, palm reader. You can make TV. You can buy OLED TV, and they have a very good image, very good contrast with respect to the older technologies. You can buy this in many shops nowadays. And it's not yet on the market, but what you can start thinking is to fold, to make flexible display. And here, the things have progressed tremendously over the years. So in 2002, this was the first prototype of a foldable display. I hope you will see the movie. Yeah. So it was monochromatic. It was just a green emitter, and you could see that you could bend the device without losing the quality of the picture. So there was really a future for flexible displays. And it's not yet coming on the market. It's close to it, but recently the company LG Electronic has just disclosed, and I let you have the surprise. So they disclosed the first foldable TV. And have a huge screen, have a foldable display. See. I stop here. It's already sold in Japan. And now recently, to go more into the science fiction, Lenovo has reported a flexible PC with an OLED display. So you can really bend your screen, and this is the first foldable PC that has been shown recently. I told you that you can print over large areas, which you cannot do with the LED technology, with the inorganic materials. And this is the kind of signal that you might make with the OLED technology, like big panels to show the exit in case of fire in the building. So you can print very large areas, which is quite interesting for some application. Do we have more challenges for OLED? Yeah, we have. And one big challenge is to make white lighting, to make white light with an organic light emitting diode. Currently, this is dominated by the LED technology, by the inorganic material, but it's a huge market because this is a picture of the world during the night, and you see that 20% of the electricity used is basically used for lighting. And so lighting is a huge market. So can we make efficient OLED giving white light? The answer is yes. So compared to the old technologies like the bulbs, the halogens, the fluorescent tubes, they have an efficiency of about 80 lumens per watt. And now the OLED are above 100, much above the 100 lumens per watt. This is shown here for a green OLED, but now this has been done also for white OLED. Of course, you cannot at this stage compete with the LED, the inorganic material, but you can find maybe some application where the flexibility, the low cost will be used for some design, for some specific niche. This is an example of a panel emitting white light, and basically the main problem of OLED is that you cannot inject a large current, and so the brightness is not as good as a LED display. And this is why, to compensate, people are playing with a much larger, well, significantly larger areas for the white panels. It's about 15 over 15 centimeters square. And right now there are some products starting for the designers to make huge panels on walls, to make ear lighting panels. This is already sold in Japan. And there are new concepts in development where you would have the white emission coming from a transparent device, and you could get information appearing on your screen in the TV, on the windows when you take the train. So these are some applications where you could use the OLED, because you can make a transparent device if you choose carefully all your components. So we talk about generating light by injecting charges. Of course, we could think about the opposite. This means sending light and creating charges. And this is the principle of organic solar cell. And this is also a big area where we have not yet big commercial products, but where organic materials are very promising. So in a simple, let's make some science first. In a simple architecture, you would have, as before, two metallic electrodes, the organic layer, a glass to give the mechanical robustness. So the light is entering into the device and is absorbed by, let's say, one of the material. We will call it the donor. And when you excite in a simple picture, you transfer an electron from the HOMO to the LUMO, and you create what we call an excitation, an exciton. Now the thing is, in contrast to all the inorganic material, this exciton is very stable. It's very difficult to have the electron moving to the left and the hole, the electron to the right and the hole to the left, to break the excitation into charges. This is not spontaneous, basically because the organic materials have a low dielectric constant, and so they are not screening enough the Coulombic attraction between the hole and the electron. And so you have to find a trick to fight against this binding energy, which is huge. And the trick is to use a second material that we will call the acceptor. And basically, when you excite one molecule, you generate your excitation. Then the excitation has to move, to migrate, and to reach the interface with the acceptor. And here, the electron here is happy to jump down to the LUMO of the acceptor because it's way below the LUMO of the donor. And thanks to that, and thanks to this offset, you can break the excitation into charge carriers. So this is the principle of organic solar cells. It's also like a PN junction in silicon-based solar cell. Of course, the bilayer that I showed you here is not the best architecture because when you generate your excitation, you want to make sure that your excitation will reach the interface. But you have to know that this excitation is living for 1 nanosecond and is traveling about 5-10 nanometers during its lifetime. And so if they are produced far away from the interface, well, they will not be exploited to make a current. So this is a problem of this bilayer architecture. We will come back to that. So it was not easy to design an organic solar cell, and it's still not. There are many challenges that we had to face. And the first one is to absorb efficiently the light emitting from the sun. So what you see here on this spectrum is the spectrum, the emission spectrum of the sun that we are getting on Earth. Sometimes you have big absorption peaks here. This is coming from the gas in the atmosphere, like ozone, water, and so this is really what we get from the sun that we need to absorb to make electricity. And if you take a typical polymer that we are using in a Oled display, this guy, for instance, you see that the overlap between the emission and the absorption is very bad. Actually, if you look at this is the integrated flux that we get from the sun. And if we just take the onset here, you get only 20%. So if everything goes well, this kind of polymer with a gap of 2.1 eV can only absorb 25% of the light coming from the sun. So we need to find polymers, materials, where the absorption will be shifted significantly to the red to promote a very good overlap. And basically we want a band gap for those materials of about 1.5 eV. But this is not easy to find, and so this was a big challenge for the synthetic chemist. Initially, all the devices were built with PCBM, fullerene derivatives, because they are very good acceptors. Their LUMO is very deep, so you can have very efficient dissociation of the excitation into charges. But the efficiency, which means what we call the efficiency, is the electrical power generated over the light power absorbed by the device. And well, basically the efficiency were saturated around 10%, which was good, but not good enough to compete with silicon and other well-established technologies. And then people started to realize maybe 4 or 5 years, well, a few years ago, that PCBM at the end is really not the best candidate because first, it's poorly absorbing where the sun is emitting. And it's very difficult to make some chemistry on this ball to tune the LUMO energy, which is quite useful for optimization. And this with light, this ball is also unstable and can dimerize and make complex molecules that are not useful for the application. So recently, a new generation of acceptor has appeared. They look like that. So these are small molecules. And starting from 2016, they have started to behave very well, much better than C60 very recently. And nowadays, we are reaching PCE, so power conversion efficiency, reaching about 18%, which is a fantastic number for an organic technology with all the advantages of processing. And so this is really a revival of the field, and now there is a new boost to understand those materials and to make organic devices with very high efficiency, maybe not competing directly with silicon, but that you can exploit in many applications where you want to play with the flexibility, and we'll see that in the following. Another main advantage of the non-ferrine acceptor, this new generation, is the stability, because you want a stable device, of course, when you're going to install it. And you see that this is typically with C60, you drop very quickly the inefficiency, which is bad for the device. With those new material, the chemical stability is also very good, and you get very almost constant efficiency after 2000 hours, which is very good for product. The last problem I told you is that you don't want to play with a bilayer because you are going to lose many excitation. They will not be converted. And so the trick is to make a very intimate mixing of the two materials, the polymer and the acceptor. And you want to make what we call a bulk heterojunction, to have a nanostructuration so that you're sure that when you make an excitation, there is always an interface nearby. But this is very tricky to make the right morphology because okay, it's something kinetic, and you want to find the right condition. You can play with the solvent, the concentration, the temperature. So it's very, very tricky to find the right composition. And here a very useful tool is atomic force microscopy, because when you make the blends, you can go with this microscope and you can probe the surface, of course, but you can probe and distinguish the two components. And for instance, here you see that we have taken the same materials with the same ratio in solution, and we have deposited a film, but in toluene or in chlorobenzene, so just changing the solvent. Here in toluene, you have a segregation, but you have big clusters. And so this is not the nanostructuration that we are expecting. In chlorobenzene, you see that there is a much better mixing of the two components, and as a result, the efficiency of the device is much better. So it's bilayer is very easy to make, but you lose a lot of excitation, and it's very challenging, but this is what we have to do nowadays, is to find the right condition to have this kind of very homogeneous morphology. So there are not too many products so far. There was a plastic bag commercialized, but it was not a major success. This was just to show the potential of the technology. Here the cover is an organic solar cell. It's red because the polymer has a red appearance. But the good thing is that you can bend the bag, it's no problem. And in this product, there was like a connection to walk anywhere and to charge your phone or a small electronic equipment while you are walking anywhere in the forest, in a city. Okay, now there are more applications tested. This is in San Francisco, a bus shelter. And you see here that the organic solar cell can really be deposited on any kind of substrate. So it doesn't matter the texturation because we can conform to the substrate that we want to use. And so this is used since more than 5 years. It's stable, and it's just powering a monitor to tell about the schedule of the next buses. You can think about portable chargers for reading with your iPhone. Okay, it's not nice, but okay. This is a nice one here. This is a medical tent. So the idea would be to sew the organic solar cell on a textile and to make this kind of autonomous tent, and all the roof could capture the light and generate electricity, maybe to power some medical equipment. So this is a nice application to contact the solar cells to a textile because it's flexible and you can make very original product that silicon cannot make. Not too much product, as I told you. There is one company emerging in Germany, which is called now Obvious, OPV, Obvious. And they start making some prototypes. This is a window for an architectural product. This is a nice window, but each leaf here is actually an organic solar cell. So this window can capture the light and make electricity. And recently, they have also disclosed some concept like the solar trees that you can use to capture the light and generate around you some electricity. So we are going to it because now we have a major boost due to the new generation of acceptors. And I think maybe in the next year, we will have more and more focus at the industrial level on this kind of OPV technology. The installation, yeah, this is nice. This is done by the Danish Technical University. It's quite easy to install an organic solar cell compared to the silicon panels because you have just to you buy a roll of the product and you have just to deposit on any kind of panel. So yeah, the processing is a key advantage for this technology. So here it's a kind of concept where you shine light and then you break it into electrical current. And actually this idea of playing with charges and light has also been used to make chemical sensors with the same conjugated polymers. This is a nice example, a funny one, as you will see. So this is a landmine detector made with conjugated polymers developed for the US Army. and you will see that this guy is taking a lot of risk. So basically you have a polymer, a conjugated polymer, which is very, very emissive. And there are side groups making kind of channels for small molecules to go inside the molecules. And so when the polymer is in the pristine state, you excite the chain, you get the homolumo excitation, and you have a very efficient light emission in return. Now, if you scan any zone and you have TNT around, like vapor of the TNT coming from the landmine, TNT can penetrate into the channels, and then TNT is a strong acceptor. And if you excite the polymer, the electron will be transferred to the LUMO of TNT, and then you kill the luminescence. And so if you don't see the luminescence, this means that you have a landmine next to you. This is why this picture is not realistic, because this guy, if he doesn't see any light, he should be quite scared. The detection limit is amazing. It's 10 minus gram. The problem is the selectivity. If there are something resembling TNT, it can also be used to make the same kind of quenching of the light emission. But this is a huge family of new application. You can go to the biological world to make biosensors with the same principle. So if you want to see the presence of avidin in a sample, avidin is a protein. What you can do is to connect biotin. Biotin is a vitamin with a very specific recognition to avidin, and you connect biotin to this molecule, methylvialogen. This is an acceptor. And the third player is a conjugated polymer, soluble in water, so thanks to these charged side chains. And the story goes like that. If there is no avidin, the methylvialogen will be attracted by the negative charge here. And so if you excite the polymer, there will be an electron transfer to methylvialogen and no light emission. Now, if the biotin is, if there is avidin, biotin will be captured by the avidin. You will have the free polymer in solution, and then if you excite the polymer, you recover the light emission. So this is a very simple diagnosis to make to probe the presence of avidin. So we talk about solar cell, we talk about light-emitting display. There is a third big application, and this is to make organic field effect transistors. So a field effect transistor is basically the building block of any electronic circuit that we find today to make a logical operation, to treat data, to play with numbers. Every time you have some logics to be done, you need a field effect transistor. And of course, nowadays they are typically based with silicium. So in organic field effect transistor, you have three metallic contacts: the source, the drain, and the gate. Here it's an insulator. You will see why after. And this is the organic layer that we drop between the source and the drain. And initially, okay, if you look at the source, we have the Fermi energy of the metal, and we have the HOMO and LUMO of the organic material. And there is no injection because there is a barrier in both cases. So now let's assume that we are going to make a positive charge, a positive bias at the gate, plus, plus, plus everywhere. What we are going to do is to put a negative charge on the source and also on the drain. So the source and the drain will be at a more negative potential than the gate. So you are going to raise the Fermi level and to inject electrons in the LUMO. And all the electrons here will be attracted by the plus charges, but since there is an insulator, they cannot recombine. And so you have a lot of charges here in the channel. And if you apply a source drain bias, you can have this current flowing in the channel, and you have a current in your device. So the FET is like a valve. It's an on-off system. If you, with the gate, you can decide if there is a current or not flowing into the transistor. So this is the basic of the modern electronics that we are using for electronic circuit. So can we make nice application? Yes, this is not yet done, but there is a new fashion is to make radio frequency identification tags. So the principle, you know, those little tags in the shop. You have a scanner, you send a radio signal, it's absorbed by the tag, and then a new radio signal is sent back to the scanner, and Don't ask me how, but with this signal, you know basically the price of the product, you know its code number, you know the expiration date for some food, and this tag could be made very cheap and very flexible by using organic transistors. This is a concept here, but okay, it's not coming yet on the market due to stability issues, but this could be an idea to have flexible tags that could be used, maybe not in supermarket first, but to track suitcases in the airport, like blood samples or many other applications. In many displays, like in a TV display, actually each pixel is driven by a transistor to control the quality of the image. And if you have all your transistors made with an organic material, then you could have what we call an organic active matrix for your display. So we could think about, and we will go to that, we could think of foldable display like electronic papers, where you would use as the active matrix organic field effect transistor to control each pixel. And you would need something to make a picture on the top layer. And here there is a very nice technology called e-ink, electronic ink, that has been developed. And the principle is very simple. You have a large number of capsules, big capsules, and they are containing a blue dye, an organic molecule, and some negatively charged white TiO2, the titanium dioxide particles. So if you apply a bias in this way, the negative particle will be repelled to the bottom, and you will see all your capsule in white. If you reverse the bias, you have a plus on top, you attract, it will be in blue. And now if you put the plus here, you attract all the nanoparticles to the top, and you have a white pixel. So it's a very, very simple way to make a on-off, well, a contrast with two different colors, black and white, or here blue and white. Now, if you put everything together, what you can make is an electronic paper. So this is a concept of electronic paper developed by Plastic Logic, a company in the UK, where you have e-ink used to make the display, and you have the active matrix to drive, to control the quality of the picture. And with this guy, you could download every morning your PDF with the newspaper and read it when you are going to work in the train, or it's like a transporting newspaper. But can it be flexible? Yeah, of course. Now, it's not yet on the market, but it's also in development. And I'm going to show you, okay, it's close to science fiction, but what has been done recently in Plastic Logic. So there is a part with a lot of discussion that I will try to skip. But this is a flexible electronic paper. So this is really e-ink technology coupled to an active matrix with an organic field effect transistor. So this could be like the newspaper that could be sold in the future. It's touch sensitive, so you can have different menus. You have option. It's really a completely independent electronic paper. If you bend the, okay, this is another application for, it's like a wrap that you put around your okay, you understand, just to monitor your health when you run, for instance. You can also bend the corner of the display to get some option. But there is, okay, this is maybe the future of the newspaper. It can be animated. You can see movie. And now this is really science fiction. So this guy has here three electronic papers, completely flexible. One here with the inbox. And here there is, on this one, there is a picture. And in the middle one, he would like to reply to a mail that he just got. And don't ask me about the interest right now, but at the technological level, it's quite impressive. So he's touching the middle paper with the one on the left, and it's transferring the email. So they are communicating between them. If you bend the corner, you have a keyboard. And if you want to transfer the picture, you made it like that. So these are connected electronic papers, which is quite impressive for this technology. there are other nice application. If you take your finger and you touch the OFET, the organic field effect transistor, you are going to compress the organic layer. And if you compress it, you are going to change the electrical conductivity in the channel. And so OFET can also be used to make like touch sensitive devices. And this has been done in Japan, for instance, to give to the robots what they were missing. This means the sense of pressure, that if you shake the hands of a robot, it will know if you do it in a light or in a very strong way. So it's a kind of artificial, so all the connection here are made with OFETs to give the sensation of touch to the robots. It will never compete with the human skin, because in this application you have 16 sensors per centimeter square, like we do have like 1,500 per centimeter square. But this is also a possible application for people who suffer from a severe burning damage of the skin. We could maybe reconstruct an artificial skin and they could recover the sensation of touching. Before closing, I would also like to open two new emerging fields for organic electronics. This is very new, but there are many interesting perspectives for the future. So my title was When Organics Meets Electronics, and now it is When Organics and Electronics Meets Biology. And we have a new emerging area that is called organic bioelectronics. So the idea is to connect living organism, like the biological world, to the electronic world, specifically organic electronic, because it's flexible, it's quite compatible with the living organism. And this could be used to first just monitor, to make sensing, to make diagnosis, and perhaps even better to act on the organism, on the living organism, to make some therapy, which would be referred to as bioelectric medicine. So let me show you an application. Here we're going to play again with organic field effect transistor, but in a very different way, because here we have once again the source, the drain, the organic material, and the organic material is in contact with water. This is the place where biology is living, basically, and we have a gate in the water solution. And there is a nice application that has been shown recently. People have succeeded in monitoring the communication between neurons in the brain. And actually, we know that when neurons communicate, they exchange sodium cations. And so when we put this transistor, it's called an organic electrochemical transistor, in contact with the brain, we will have the cations here in the solution. And at a given stage, we can apply a bias to the gate, like a positive bias, and the cation will be pushed into the organic layer. And they are going to change the electrical conductivity of the organic layer. And this change is monitoring basically the communication between the neurons. Now, this might be interesting now, because, for instance, when someone is in epileptic crisis, epilepsy, we know that the neurons start exchanging much more cation between them. And so with this kind of devices, we could monitor the communication between neurons and prevent and detect that a crisis is going to occur. So artificially, we know that we can hyperexcite the neurons by injecting potassium, K+. And here you see that when you inject potassium, the neurons start to communicate like crazy. You have a lot of spiking activity, and this is it could be the sign in a real body that there is an epileptic crisis going on. And so this is the monitoring part. This is nice because you can really monitor if everything is going okay between neurons. And now I won't show you that because it's more difficult, but people have also developed recently an ionic pump, also based on organic material. And the thing is that when we detect a crisis, this ionic pump can inject on demand a medicine which is going to stop the crisis. Like we can inject dopamine into the brain, and this epileptic crisis will be stopped very quickly. So this is a new field for us, for the field, and we want to interface the organic electronic technology to the living organism to monitor and maybe to help them. And finally, something maybe more for the physicists, if they are. So far in electronics, we are familiar with the fact that we have electrons moving, and in a transistor, we can open or shut down the flow of electrons. So we have a binary signal, like 0 or 1, the current is flowing or is not flowing. But there is another way to make a binary signal. It's to play with the spin of the electron, because you know that each electron has a spin up or a spin down. And if you could play with that, you have a new kind of devices with a lot of possible application, a lot of possible operation. And here we are entering into the world of Spintronics. So Spintronics is fascinating. It's not an easy field to go in, but I can show you a simple example of what you can do with the world of Spintronics. So let's say that you have a current of electron flowing in a metal like a copper, and along the way you put a ferromagnet. So a ferromagnet is basically for many material and molecule. If you look at the number of electrons at each energy, typically you have the same number of spin up and spin down at whatever is the energy. In a ferromagnet, it's different, because you see that for some energies you have a lot of spin up but no spin down. So you have like a spin polarization in the material. And it goes like that when this current is flowing across the ferromagnetic layer. Only the spin parallel to those at the Fermi level can cross this layer. So here, before I have the spin up and the spin down, but only the spin up can cross this ferromagnetic layer. Basically because at the Fermi energy, I have a majority of spin up. Now, if you change the magnetization of the ferromagnet, you will reverse the blue and the red region. You will have a majority of spin down at the Fermi level. So let's say that we put two ferromagnets with different magnetization. So here only the red spin can cross, and here to cross you need to be spin down, but they're only spin up. And so there is no way to try to cross the second ferromagnet. And so you see that there is no current flowing across the device. And this is just controlled by two electrodes, not three like a transistor. Now, if you take two ferromagnets with parallel magnetization, in this case, in the first step, you just inject the spin-up electrons. So you have what we call a spin polarized current. But this current can also cross the second ferromagnet, which is favoring the spin-up. And you do have a current flowing across the device. This is called a spin valve. It's a valve that controls the flow of electrons based on the spin of the electron. And this concept of controlling the current is also connected to the concept of magnetoresistance, because by just changing the magnetization of the second ferromagnet, you can control the current flowing across your device. So it's called a magnetoresistance. And this is actually what we find nowadays in all the data storage application, like in the magnetic recording, in your hard disk, in your computers. This is those kind of spin valves that you find in your devices, but they are nowadays typically based on inorganic material. Now, of course, to get a good device, when you inject the spin up here, you want your spin up to go fast across the layer here, but you don't want your spin to flip over during the path, during the travel, because otherwise you're losing your principle of selectivity. So you want the spin here to go fast and to keep the orientation of the spin. And here the current inorganic material are very, very good to provide a very fast speed for the charges, but they are very bad in keeping the orientation of the spin. So this is what you will see in my last slide. Typically, there are two key parameters: the spin relaxation time, how fast is the spin going in the opposite direction, which is very bad for the device, and how far the charge can go before the spin is flipped. And you see that all the inorganic materials are very good to give rise to long diffusion length, but they're very, very short spin relaxation time. And now there might be a future for organic spintronics, because we know that since we have very light atoms in organic molecule, there is a very, very slow spin relaxation time. So we keep the spin over a large distance in organic material. But the problem right now is that the diffusion length is quite limited. If it would be here, we will have a new generation of material, of organic material for spintronics. But this is maybe what we will see in the future. Okay, I think it was a very dense, not too long journey. I think it's time to land on. And so thank you for your attention. And now we'll be happy to answer any question that the young chemist will submit me. Okay, thank you.
Thank you, Jérôme, for your presentation. I am the one we will read the questions, so there is some of them. I will start with the first one. So here we have the first question from an anonymous one, and he asked, would it be possible to create and use conductive biopolymer for the same applications that were presented?
You mean electrically conducting biopolymers? This is the question, right?
Yeah, for conductive biopolymers, yes.
Okay. The thing is that with if you want to get a very good electrical conductivity, you need a conjugated path, a very well-defined conjugated path. In many biopolymers, you do have a lot of conjugated electrons because you have in biopolymers, you have a lot of carbonyl amide function. But the thing is that they are not connected together. They are always like side chains, and there is no full pathway for electron transport. If you want them to hop from conjugated groups to the neighboring one, then it will be extremely slow and it's not the best idea. So you could have a small charge transport, because people have claimed that you can have a charge transport in DNA, because you know that the nucleic bases, they are made of pi electrons and they are stacked, and so this is a kind of pathway for electron transport. And people have claimed that electron can be transported along the stack of DNA base pair. And it's quite controversial, but I think it's true for a short distance. So with biopolymers, the first step would be to inject the charges. It will be very, very difficult, because I guess that with a conjugated polymer, your HOMO is around 5 eV. With the standard polymer like polyethylene, like I guess many biopolymers, the HOMO is at minus 10 eV. And so it's very difficult with a metallic electrode to go and remove electrons 10 eV below the vacuum level. So I think it's difficult, I think. What you could do is to have like a composite, where you have a biopolymer that you would mix with a conducting polymer. This maybe would be the best solution.
Okay, thank you. So next question is from Stefan. Could you comment on the difficulties the industry has to develop polychromic electronic paper, and what is the big deal?
Polychromic. Polychromic, okay. Big deal. Boom, boom, boom. Typically, in your this I didn't say, in your device, when you I don't know what Stefan means by polychromic. Sometimes there are material when you make a crystal. When they crystallize, they will adopt a very specific color. And if you change the organization of the molecule in the crystal, you can generate a different color. So this is called crystallochromism. This is interesting, but the thing is that if you make an application with electric current, there is always a big issue, is the Joule effect, meaning that you're going to release a lot of energy, and this is going to increase the temperature of your device. And you don't want your color to change because the temperature is increased. And I think this is if I understand well, this is an issue for taking the same material in different morphologies to get a very specific color. What I didn't mention also is that if you want a very bright emission for all the materials here, you don't want them. You don't want to make a single layer only made with this material. Otherwise, there are many detrimental effects which are going to kill the fluorescence. So typically, those molecules, those emitters, are encapsulated in a matrix, and typically the matrix is 95% of the film, and those emitters are like 5%. So making color is not a big issue. I think that, I can comment also that the most difficult color to obtain is the blue, because blue is a very high energy for light emission, and this energy can also be used to make photochemistry on the molecule to start degrading the molecule. And so there is a big issue, but it's also the same for the LED technology, is to make a very good blue emitting material which is stable over many, many hours of operation. So blue is the problem. Maybe this was the question of Stefan. Or if you want to play with crystallochromy, the temperature rise is a problem. Max?
Sorry, I didn't turn on my microphone. I was talking alone, so okay. Another one, is it possible to have elastic displays that you could stretch to make bigger or smaller?
Yes. This is developed right now. If you are interested, you can look to the work of Zenan Bao at Stanford University. She is making electronic skin, and electronic skin should be stretchable. Of course, with the kind of display that I showed you today, it's difficult to stretch them to make something elastic. So Zenan Bao is making stretchable conductive plastics and to make like artificial skin. But I think she is using a mixture. There are carbon nanotube to give rise to the conducting properties, and then there are elastomers to give rise to the elasticity. So if you make what I showed you today, no, you cannot make stretchable, but they are developing technologies, to make, for instance, the artificial skin. This is a huge project in US, and there, she can stretch a lot the sample while keeping the same electrical conductivity. But I think these are not the same materials involved at this stage.
Okay, and we'll just come back on the last question from Stefan with electronic papers. He said that there is only black and white electronic papers. Why not several colors?
I don't know. No, we should ask. I don't know. There are no fundamental reasons for that. I think it would be much more expensive, I guess, to make it's a prototype so far. So I think they didn't put too much effort to get a full color display. But I think it's now available in Plastic Logic. What I showed was black and white, but I think now they are starting to make a fully color display. But if the technology is not accepted by the public, then maybe it's not worth investing a lot of money. So I think at this stage they are trying to make prototypes, nice product, but I don't see it's like you just change the dye that you have in the capsule and you could get any color you want. So I think it's just a matter of simplicity for the first testing.
Okay, so I will now finish this presentation with the last question. I will take the question of Volo. He has two questions. He told us that Samsung stated that they no longer consider OLED for big screen and prefer QLED. Could you comment on that?
QLED is a new emerging technology where you use quantum dots as light emitters. So quantum dots are nanoparticles made of inorganic material like cadmium selenide. The beauty of these nanodots is that with polymers or with organic material, if you want to go from red to blue to have different colors, you have to play a lot with the chemical structure to change the substituent, to change the topology of the backbone. With the quantum dots, you can just change the radius of the nanoparticle, and by changing the radius, you change directly the color. So this is one advantage. You have just to tune a button to change the size of the nanoparticles. The second one is the stability, because of course a quantum dot are very robust system. They are not affected as much as organic molecule with pi electrons. So for a matter of stability, for a matter of color tuning, I think they are quite good. Now I'm not an expert in this field. I think the main problem could be the charge transport, because you still need to have charges hopping from quantum dot to quantum dots, and this is difficult because the area in contact between two quantum dots is small, and so from what I knew, I think the charge transport was really the limiting step, because if you have any kind of capping on the quantum dot, then it will be difficult to transfer electrons between neighboring dots. But I know that there is now a QLED TV already commercialized, even in Belgium, I think. And okay, well, I'm not sure that the flexibility would be as good as with organic material, but maybe this will compete for some specific application like TV display. But okay. To be honest, the people working with quantum dots and people working with organic light emitter, they are living in two different worlds, and it's quite unusual that we meet all together. So I'm sure we are facing the same issues to get a very good divide, but we don't talk too much because these are quite separated fields. But we should maybe interact more in the future.
Okay, and its last question was for organic transistors. What is the method used in order to accident them? Is it lithography, and is there a minimum writing size?
To write them, yeah, this is the same issue as the current electronics. So you can downscale the size of the transistors with lithography. It's typically made with photolithography, or you can go even below by using new techniques. So the processing of basically of the circuit to draw the lines and everything is exactly the same as for a silicon-based transistor. The only difference is that when you have your electrodes defined and settle on your board, then you can drop your organic material with a simpler technique. Like you can just drop you can just put a drop of solvent with the material inside, or you can evaporate in the right place. So I think we have the same regarding the size. We have the same issue as the current electronics, yes. But we don't, for sure, organic transistor will never compete with the processors that we have in our computer. So I don't think that we are interested to downscale a lot the organic transistors. We want to use them in application where silicon cannot make a big impact. When you want specifically to promote flexibility, then you're a winner, and you don't need to downscale a lot your application.
Okay, thank you, Gigi. Thank you, Jerome. Sorry for this best presentation. It was very interesting to know all this information on how to make OLEDs and all of the polymers were very interesting to this field. So thank you very much for this very good and pedagogic presentation. Just to remember for all the people, just stay tuned on our Facebook pages about all the activities from the Jeunes de la Société Royale de Chimie, and don't forget to participate with our short presentation with all the videos. So thank you very much, and see you next time for next activities and the next webinar. Thank you very much.